Front-end tool data preparation. The board designer has prepared his layout on a computer-aided design or CAD system. The Gerber files define the copper tracking layers, 4 in the job we are following, as well as the solder masks and component notations. First we check that data meets our manufacturing requirements. These checks are mostly done automatically. We check the track widths, the space between the tracks, the pads around the holes, the smallest hole size, etc. The engineer can also check and measure individual areas where he wishes. Once the data is verified as good, he will output all the tool files needed to drive the machines that will make and test the PCB. Preparing the photo tools. We use laser photo plotters in a temperature and humidity controlled darkroom to make the films we will use later to image the PCBs. The photo plotter takes the board data and converts it into a pixel image. A laser writes this onto the film. The exposed film is automatically developed and unloaded for the operator. We've generated one film or photo tool per PCB layer. Now the films are registered with each other so that the different layers of the PCB will be perfectly aligned. We do this by punching precise registration holes in each sheet of film. The operator puts the film on the table of the punch and then micro-adjusts the table until the targets on the film are exactly lined up with the targets on the film punch. She then punches each sheet of film with the registration holes which will fit into the registration pins in our imaging equipment. Print inner layers. To produce the inner layers of our multi-layer PCB, we start with a panel of laminates. Laminate is an epoxy resin and glass fibre core with copper foil pre-bonded onto each side. The first step is to clean the copper. We print the panels in a clean room to make sure that no dust gets onto the surface where it could cause a short or open circuit on the finished PCB. The clean panel is coated with a layer of photosensitive film, the photoresist. The bed of the printer has registration pins matching the holes on the photo tools and in the panel. The operator loads the first film onto the pins, then the coated panel, then the second film. The pins ensure that the top and bottom layers are precisely aligned. The printer uses powerful UV lamps which harden the photoresist through the clear film to define the copper pattern. Under the black areas the resist remains unhardened. The clean room uses yellow lighting as the photoresist is sensitive to UV light. Outside the yellow room the panel is sprayed with a powerful alkali solution which removes the unhardened resist. The panel is pressure washed and dried. The copper pattern we want is now covered by the hardened resist. The operator checks a sample of the panels to make sure that the copper surface is clean and all the unwanted resist has been removed. You can now see in the blue resist what will be the copper on our inner layer panel. Etch inner layers. We remove the unwanted copper using a powerful alkaline solution to dissolve or etch away the exposed copper. The process is carefully controlled to ensure that the finished conductor widths are exactly as designed. But designers should be aware that thicker copper foils need wider spaces between the tracks. The operator checks carefully that all the unwanted copper has been etched away. Next, we strip off the blue photoresist which protected the copper image. So now we have the exact pattern required. The operator checks that all the photoresist has been removed. Register punch and automatic optical inspection. The inner core of our multi-layer is now complete. Next we punch the registration holes we will use to align the inner layers to the outer layers. The operator loads the core into the optical punch which lines up the registration targets in the copper pattern and punches the registration holes. We won't be able to correct any mistakes on the inner layers once we've assembled the multi-layer, so we now give the panel a complete machine inspection. The automatic optical inspection system scans the board in broad strips and compares it with the digital image generated from the original design data. Any errors are displayed on the screen. Layup and bond. The outer layers of our multi-layer consist of sheets of glass cloth pre-impregnated with uncured epoxy resin, or pre-peg, and a thin copper foil. The layup operator has already placed a copper foil and 2 sheets of pre-peg on the heavy steel base plate. Now he places the pre-treated core carefully over the alignment pins. Then he adds 2 more sheets of pre-preg, another copper foil and an aluminium press plate. He builds up 3 panels on the base plate in the same way. He then rolls the heavy stack under a press which lowers down the steel top plate. He pins the stack together and rolls the finished stack out of the clean room into a rack. The press operator collects 3 stacks on a loader and loads them into the bonding press. This press uses heated press plates and pressure to bond the layers of the PCB together. The heat melts and cures the epoxy resin in the pre-preg, while the pressure bonds the PCB together. The process is computer controlled to build up the heat and the pressure correctly, hold it, and then to cool the press down. In this way we ensure a permanent bond that will last the lifetime of the PCB. Our board has 4 layers, but complex PCBs for defense, avionic and telecommunications applications can have more than 50. These may include sub-assemblies of cores, pre-pregs and foils drilled and plated before being assembled into the final PCB. Once the cycle is completed, the press operator unloads the press and carefully rolls the heavy stacks into the clean room. Here the layup operator depins the stack and removes the top plate. He unloads each of the panels from the stack, removing the aluminium press plates used to ensure a smooth copper finish. The copper foil is now bonded in place to form the outer layers of the PCB. Drilling the PCB. Now we drill the holes for leaded components and the via holes that link the copper layers together. First we use an X-ray drill to locate targets in the copper of the inner layers. The machine drills registration holes to ensure that we will drill precisely through the center of the inner layer pads. To set up the drill, the operator first puts a panel of exit material on the drill bed. This stops the drill tearing the copper foil as it comes through the PCB. Then he loads 1 or more PCB panels and a sheet of aluminium entry foil. The drilling machine is computer controlled. The operator selects the right drill program. This tells the machine which drill to use and the XY coordinates of the holes. Our drills use air-driven spindles which can rotate up to 150,000 revolutions per minute. High-speed drilling ensures clean hole walls to provide a secure base for good plating on the hole walls. Drilling is a slow process as each hole must be drilled individually. So depending on the drill size, we drill a stack of 1 to 3 PCB panels together. We can drill holes down to 100 microns in diameter. To give you an idea of the size, the diameter of a human hair is about 150 microns. Drill change is fully automatic. The machine selects the drill to use from the drill rack, checks that it is the correct size, and then loads it into the drill head. Once all the holes are drilled, the operator unloads the panels from the drilling machine and discards the entry and exit material. During bonding, excess resin from the pre-preg is squeezed to the edge of the panel outside the image area. This excess is now cut off on a computer-controlled profiling machine. The operator loads the panel onto the bed of the machine and selects the correct program with the XY coordinates of the path for the cutter to follow. The drilling machine uses the points of the drill, but the profiling machine uses the specially patterned shank. The cutter mills out the final profile for the production panel. The drilled panel is now ready for plating. Electroless copper deposition. The first step in the plating process is the chemical deposition of a very thin layer of copper on the hull walls. The operator clamps the production panels into the jigs. The line is fully computer controlled and the panels are carried through a series of chemical and rinsing baths by the overhead crane. Almost all PCBs with 2 or more copper layers use plated through holes to connect the conductors between the layers. A good connection needs about 25 microns of copper on the walls of the holes. This thickness must be electroplated, but the walls of the holes are non-conductive glass cloth and resin. So the first step is to deposit a conductive layer over the hole walls. We use electroless copper. That is, we deposit chemically a layer of copper about 1 micron thick over the walls of the hole, and incidentally across the whole panel. This is a multi-stage process, as you see from the video, with washing steps between the stages. We pre-treat the panel, then we seed the whole wall with microparticles of palladium, and finally deposit the copper. Image the outer layers. We image the outer layers in a clean room to make sure that no dust gets onto the panel surface where it could cause a short or open circuit on the finished PCB. The panel is first coated with a layer of photosensitive film, the photoresist, which is hot rolled onto the copper using a cut sheet laminator. The laminated panels are collected by an automatic rack. The clean room uses yellow lighting as the photoresist is sensitive to UV light. The bed of the printer has registration pins matching the holes to the photo tools and the panel. The operator loads the first film onto the pins, then the laminated panel, and finally the second film. The pins ensure that the top and bottom layers are precisely aligned. The printer uses powerful UV lamps to harden the photoresist, so the photo mask is clear where we want the resist to harden and black where we don't want resist. The mylar film, which protected the photoresist, is now removed and the imaged panel is conveyed out of the clean room and through a developer which removes the unhardened resist. For inner layers, the copper pattern we want was covered by the resist. For outer layers, it is exposed, ready to be plated. The operator now checks the panels to make sure that the copper surface is clean and all the unwanted resist has been removed. Plating. Next, we electroplate the boards with copper. The operator loads the panels onto the flight bars. He checks all the clamps to ensure a good electrical connection. The panels themselves act as cathodes for electroplating, and we can plate the whole walls thanks to the conductive carbon layer already deposited there. The operator starts the automated plating line. The copper surface of the panels is cleaned and activated in a number of baths and then electroplated. The whole process is computer controlled to ensure that each set or flight of panels stays in each bath exactly the right amount of time. You can see the copper anodes in their bags. To ensure good conductivity through the holes, we need to plate on average of 25 microns of copper on the whole walls. This means that we also plate 25 to 30 microns on the surface tracks. So if we start with a typical 17.5 micron copper foil, it will be 40 to 42 microns after processing. The baths are designed to produce an even copper thickness across the panel. Modern chemical solutions also have good throwing power to produce an even thickness of copper right through the hole. Once we have plated the copper onto the board, we then plate a thin layer of tin. This we will use in the next step of the process, when we etch off the unwanted copper foil. When plating is completed, the flight of panels is returned to the operator and he unloads and stacks the plated panels. He then uses non-destructive testing to check a sample of each flight to ensure that the copper and tin plating is the correct thickness. Etch outer layers. We've now plated the panel with 25 microns of copper through the hole and an additional 25 to 30 microns on the tracks and pads. The copper is covered with a thin layer of tin as an etch resist. Now we will remove the unwanted copper foil from the surface. We do this on a single continuous process line. The first step is to dissolve and wash off the resist which covers the unwanted copper. Then we remove the unwanted copper using a powerful alkaline solution to etch away the exposed copper. The process is carefully controlled to ensure that as we etch down, we don't etch sideways as well. This means that the finished conductor widths are exactly as designed. But designers should be aware that the thicker copper foils need wider spaces between the tracks. Finally, we strip off the thin tin coating which protected the copper image, so now you can see that only designed copper pattern remains. As the boards emerge from the line, they are stacked automatically. Apply solder mask. Most boards have an epoxy ink solder mask printed onto each side to protect the copper surface and prevent solder shorting between components during assembly. The panels are first cleaned and brushed to remove any surface tarnish, and then are conveyed into the yellow room. Each panel is given a final clean to remove any dust from the surface and loaded into the vertical coater. The coating machine simultaneously covers both sides of the panel with the epoxy solder mask ink. The double action ensures that the ink completely encapsulates the copper tracking. Typically now 35 to 40 microns higher than the surface of the panel. The panels are now racked and put through a conveyorized dryer which hardens the resist just enough to allow it to be printed, or tack dried. The operator checks for a complete and even coating. Next, the coated panels are imaged. For this, we use a 2-drawer UV printer. The operator mounts the photo tool films on the machine and then places the panel onto the registration pins. She checks that the film and the copper layer are precisely aligned. Mask alignment will be better than 50 microns. As with the etch and the plating resists used earlier in the process, the UV lamps in the machine harden the ink where the film is clear. That is where we need solder mask on the finished board. The imaged panels are put on a conveyor out of the clean room and into the developer, which strips off the unhardened and unwanted resist. Later, the required resist will be further hardened or cured to provide a robust and permanent coat. For this, we use a conveyorized oven in the same way in which the boards were previously tack dried. But first, the operator checks the alignment of the solder mask on the panel and makes sure that there are no traces of ink on the pads or through the holes. Even slight traces will compromise the solderability of the finished PCB. RoHS compliant surface finishes, electroless gold over nickel. The copper component pads and holes have been left clear of solder mask. Now we apply a solderable surface finish to protect the copper until the components are soldered onto the board. On this line we chemically deposit first nickel onto the copper and then a thin coating of gold over the nickel. This is a chemical process needing no electrical connections. The line is fully automated, moving the panels through a series of tanks which clean and sensitize the copper surface and then deposit about 5 microns of nickel and 1/10 of a micron of gold. Under the EU Reduction of Hazardous Substances, or ROSH, legislation, we cannot use lead in our finishes. So we offer gold over nickel, as you can see. Chemical silver, using a similar process to deposit a sterling silver finish, or lead-free hot air levelling. For this, the panel is lowered into a bath of molten tin. As it is lifted from the bath, hot air jets blast the surplus molten metal from the panel to leave an overall coating of tin about 2 microns thick. Plated gold edge connectors. For edge connectors, we electroplate hard gold. First, the operator puts protective tape on the board above the connectors. Then he mounts the panel on a horizontal electroplating bath. The electroplated gold is needed for edge connectors, which will require repeated insertion and removal. Electroless gold gives good solderability, but is too soft to withstand repeated abrasion. For this you require a hard electroplated gold. For edge connectors, we electroplate 1 to 1.5 microns of gold over 4 to 5 microns of plated nickel. So if your PCB will be repeatedly inserted into a connector, you should specify hard gold plate on the edge connectors. When the edge connectors have been plated, we will remove the tape. Silkscreen and cure. Most PCBs have a component legend to show which component goes where. Today we use inkjet projectors to image the legends direct from the board digital data. Like a conventional paper printer, the inkjet printer sprays minute droplets of ink onto the panel to generate the image. If a legend is needed on the second side, the ink is tack dried on a conveyorized heater and the printing process is repeated. The inkjet printing needs no setup. Previously we lost time preparing and cleaning silk screens for each legend printing. That is why the legend is often called the silk screen. Now we finally cure both the epoxy ink solder mask and the legend. Once this took 90 minutes in a batch oven, now it takes less than 10 minutes using a 5-stage conveyorized oven. Electrical test. We electrically test every multi-layer PCB against the original board data. Using a flyer probe tester, we check each net to ensure that it is complete, no open circuits, and does not short to any other net. The flying probe tester is easy to set up as it doesn't need to test fixture, but testing every net is slow. A faster test method is the Acceler 8. This uses 4,000 tiny probes like a brush. It builds an electronic map of the PCB from a preheated good board. Then it compares each board to be tested with its map. This cuts test times by 90%. Profiling. The final manufacturing stage is to profile the PCBs and cut them out of the production panel. For this we use computer-controlled milling machine, or a router. First the machine mills out any small slots or internal cutouts. The cutter follows the path defined in the original tool file. Next the milling head automatically picks up a 2mm cutter, checks the diameter and mills around each PCB. The brush around the milling head ensures that all the dust produced is collected by the vacuum system. The circuits are held in place by small bridges of material. We will drill through these and then remove each separate PCB from the production panel. This panel has also been V-scored. V-cut scoring. Alternatively, we can profile the individual circuits on a V-cut or scoring machine. This has 2 cutters, one above and one below the panel. Each cuts a V-shaped groove, about a third of the thickness of the material, leaving a thin web holding the PCBs together. Scoring is especially used where the customer wants his boards delivered in a panel for assembly purposes. The operator measures the depth of the cut to make sure he has set the machine to give the correct web thickness. The web should be strong enough to hold the panel together, but thin enough to be snapped once the panel is assembled. Final inspection. In the last step of the process, a team of sharp-eyed inspectors give each PCB a final careful check-over. Here, an inspector checks a customer's assembly panel. She looks for any cosmetic defects like scratches. Then she measures the panel against the mechanical drawing, checking hole diameters with a tapered probe. If everything is okay, she prints out the production release note. After inspection, the PCBs are vacuum sealed to keep out dirt and moisture. Then they are bubble wrapped, securely boxed, sealed and shipped off to the customers throughout Europe by overnight courier. The process is complete. We have followed our PCB from the customer's original design to the physical circuit board on its way to him to be assembled into his finished product.